Welcome to physics class, and today we are going to look at radioactivity part 1. By the end of this lesson, you should be able to describe atomic nucleus, then explain radioactivity in terms of natural radioactivity and artificial radioactivity, explain isotope, explain radioactive element with examples, discuss radioactive emission, then solve a little problem on half-life. Let's start with this stable isotope. You know, everything that has to do with atom and element is all about nuclear forces. Some of these nuclear forces are strong and some of them are weak. And they are all part of which we have electromagnetic force. Now, we now say that there is isotope, stable isotope. When a nuclide does not disintegrate on its own due to the proportion of proton and neutron, that means when the proton and neutron of a nucleus of a particular atom or a particular element or substance is okay, then we say that they have a stable nucleus. In that case, there will be no need for asking any of the particles to leave, because on the process of radioactivity, we are going to be looking at it in a very natural understanding. So when everybody is stable, there is no one to leave. So we say that such ones are called stable isotope. And I will also let you know what is isotope. Then we also say that they are called no radioactive elements. Such elements cannot engage on radioactivity. We will let you know what is radioactivity as we move on. Example of such elements include sodium, which is given as N sub A, and lithium, which is this one, and calcium, etc. There are other elements that are not called radioactive elements, and they are seen as stable isotope. They are okay. Everybody in the house within the nucleus is fine. But there are other kinds of elements or chemicals or whatever you see around you, which we call unstable isotope. When a nuclide can disintegrate, when they can break down within themselves on their own due to the proportion of neutron being not moderate, we now say that we have what is called unstable isotope. An example of such elements include uranium, radium, and other ones, etc. Now look at this. I brought this to show you, even though I'm going to use this to do other explanations, where a particular particle hits another particle and they break in different places. So this is what we mean by radioactivity. On the process of our lesson, we are going to explain to you different kinds of radioactivity and probably why they occur. But what I'm telling you is that for this to occur, it means two things. It's either it naturally wants to break into different places, or on their own, somebody made them to happen, which is called bombardment. So this is the idea of what radioactivity is all about. I'm also using this to show you, when we look at this penetrating power, I'm just trying to wet the ground for those of you who are seeing this for the first time. There is something we call this gamma ray. Look at this, it's moving in like a photon. If you've gone through our lesson on quantization of energy quantization, you see this first one as a photon or as a wave. This one is the alpha. It stops here, but this beta crosses the first one, which is the paper, and then being stopped by aluminium. But this one continues to the end. We are going to understand what these things are and what they are. So it means that this one is more powerful in terms of penetrating power. This one does not penetrate more. Ordinary paper can stop its movement, but this one can penetrate through a paper, but aluminium can stop it. But this particular one, which is the gamma ray, cannot penetrate through a lead. So if you don't want to be affected by this effect, you can now hide behind a lead and you'll be fine. Now, radioactivity on its own. This one is natural radioactivity. Can you imagine what is going on there? It's like everybody in this house, some people are not welcome anymore. Maybe because the room was too much to accommodate everybody inside here. Let's assume that this is the nucleus. Not assume, this is actually the nucleus. All these green and red sphere you are seeing there, they are the house, which is the nucleus. Now, some set of people are not welcome anymore. They are seen as excess to requirement. Just like in a football pitch or in a club, we say that a particular player is also not welcome. And as a result of that, one person will be asked to leave. So that is exactly what is happening here. We call this natural radioactivity. So it is the emission of an element or emission of a particle from the nucleus of an atom spontaneously on its own. Nobody is asking it to do so. So this is what it is. Let's go to this. This radioactivity was first found out by a French physicist. His name is Henri Becquerel, who studied uranium mistakenly. He wasn't doing that intentionally, but he was studying a particular thing, an uranium atom, and on the process, he realized this particular element called uranium will give out some kind of rays, just like what happened in the last place. It will just give out something on its own. Now, when that thing was given out, he found out that that kind was able to penetrate through a thick paper and affected a photographic plate placed behind the other side. Look at what I'm saying. As immediately it leaves here, it goes through and affected a paper, a photographic paper. Now, because that time, I don't think the names of all these elements were in existence at the 1896. So it doesn't know what they are. He called them radiation in terms of alpha, because I will tell you what is alpha. The name of alpha has been found. He called the other one beta. He just used Greek words to name them because he doesn't really know what they are, because it was found mistakenly or unintentionally. He called the other one alpha particle, he called the other one beta particle, and the other one was called gamma ray. And that on the process was named after him. So now, what are these radioactive elements? One, radioactive elements are those elements that spontaneously emit radiation from the nucleus. Example, like I said, uranium, radium, thorium, polonium, and polonium, and the name continues, the list continues. So studying this kind of thing, you need four-figure table because you'll be seeing them, not four-figure table, pardon me, I mean the periodic table, where you see the names of these elements. And that is why the number of elements on the Earth crust keep increasing in number, because of this radioactivity. Now, like I said, radioactivity is the spontaneous decay or disintegration of the nucleus of atom of an element with the emission of this alpha particle, beta particle, or gamma rays, or a combination of any of all, or the three, or one, or two, or all of them, and at the same time accompanies with the release of energy. So when this was found by the man we just talked about, Henri Becquerel, he named them according to what he saw at the time. Now, let's go into these two kinds of radioactivity. The first radioactivity is called natural radioactivity, which I have thrown some light at the beginning part of this lesson. I said this is the spontaneous. When we talk about the word spontaneous, it's something that is not influenced, not external influence. Without external influence, disintegrate the nucleus of a heavy element with the emission of radiation. Let's see this one more time for you to understand what I'm saying. Look at this. They give out something, spontaneous disintegration. They break down. So that is what we mean by natural radioactivity. On the other hand, there are examples of such radioactivity. I may not really go into telling you how these nuclear equations are formed, because this is just part one. We are just introducing them. But if you look at this, you realize that this is uranium with atomic number of 238 and number of proton, which is 92. So if it undergoes this radioactivity, it's going to form a new element, is going to be formed, and that new element is called thorium, which is 234 and atomic number of 90. And this is what I mean by the alpha particle. Like I told you, when Henry Becquerel found this, he doesn't know the name, so he used a Greek word, alpha, to represent such kind of radiation. But after some times, physicists and other scientists found out that this particular alpha is actually an element called helium. So this is helium given as capital H. This is the symbol of helium, which is given as 4, atomic mass of 4, and then proton number of 2. So this is helium. So when helium is emitted from uranium, a new element is formed, which is called thorium. Then thorium, look at this one. This is another kind of radioactivity, which is called beta particle. Beta particle is represented, look at this. This is beta particle. And this beta particle is 0 and -1, because, at the time it was called beta particle, but we know now this is electron. So this is the symbol of electron. When it is emitted from thorium, a new element is formed, which is 234, a nuclide. Then the same thing happens to radium, and so on and so forth. So these are all what we mean by natural radioactivity. Now let's go into the one we call artificial radioactivity. And I'm going to play this clip for you to understand what I mean by artificial radioactivity. Look at this. This uranium on its own, look at this, was not breaking, neither was it disintegrating, but something hit it. It was struck by something. We call it bombardment of a particle. Sometimes it can be called by heating. So when it is bombarded, uranium was hit by this. If you see that video, you see 1 and N. This is called neutron. This neutron, when hitting uranium, breaks uranium down. Probably we'll go into chain reaction, where we will understand more what is happening here when there is chain reaction. So this is what we mean. I'm trying to paint the picture for you to understand what we mean by artificial radioactivity. So going back to what artificial radioactivity is, the question is, what is artificial radioactivity? This is the process in which a stable, non-radioactive nucleus is changed into unstable radioactive nucleus by bombarding it with appropriate atomic projectiles like neutron and proton. Now remember, from the beginning part of this lesson, I told you that there is something we call stable isotope and unstable isotope. Those unstable isotopes can be made to be, those stable isotopes can be made to be unstable by making them to be a radioactive element by this process called artificial radioactivity. One thing I have really appreciated about scientists is whatever nature can give, they will on their own try to produce it. So they were able to produce this, and when we'll be studying nuclear physics in terms of fission and fusion, then we'll appreciate what is artificial radioactivity better. Now look at the examples of artificial radioactivity. Remember, I gave you some example of stable elements. Stable radioactive elements. Stable substances or materials. They can't go into radioactivity. But when they are struck by a neutron, this neutron was struck by this nitrogen, it produces a carbon substance, and also the release of proton. This is a proton, and this also is another isotope of uranium. When struck by neutron, produces baryon, krypton, and two more neutron, which will continue to produce more, because the more this is produced, the more there will be more nuclear reaction, and that is what leads to atomic bombing and what we call chain reaction. So this one is deuterium, tritium. When they form together, they form a helium. In fact, this is what happens in the sun. Honestly, when we be studying fission, we understand this is how the sun is continually producing energy on this process. So these are the example of artificial radioactivity. Now, we talked about isotope, we talked about stable isotope and unstable isotope, but the question is, what is this isotope? Isotopes are atoms of the same element which have the same atomic number but different neutron numbers, and hence different mass numbers. Common examples are of elements which exhibit isotopy include hydrogen, carbon, and uranium. For example, hydrogen, you can understand that we have this kind of hydrogen, and we also have this kind of hydrogen. We also have this kind of hydrogen. One thing that is different in all of them is the fact that they have different atomic mass. This is the upper one is atomic mass, this is atomic mass, this is atomic mass, because every nuclide is given as this. This is a nuclide. You know, when you don't know the values of any element, you can call them nuclide. So this is A is for the atomic mass, and this is for the number of proton. So this is what we mean by isotope. And because of this, different elements can be produced, and what is causing this is what we mean by artificial radioactivity. That is the reason why we have a lot of isotopes. Radioisotope are isotopes that are made artificially, we have said this before, by bombarding neutron, proton, or deuteron at elements. Example, this is neutron, and then this one is sulfur 34, and it produces another sulfur, which is sulfur 35, and the release of energy, very high energy. Then this is also neutron. So neutron is very important in this radioisotope or radioactive artificial part of it. And this is cobalt. Then it produces another kind of cobalt, which is an isotope of cobalt of 60 atomic mass and 27 proton number, and with a release of energy. So this is what we mean by radioisotope, and they are caused by artificial radioactivity. Now, this particular radioactive element, remember I said from the beginning part that there is no way radioactivity will occur without emission of either alpha particle or beta particle or gamma ray, or both, or even all of them at the same time. But it was found out that these kinds of emission or particle that we are giving out from these radioactive substances, some of them have different properties and they behave differently. Like I said, the alpha is just a helium atom, while beta is an electron, and gamma is a photon energy or a wave or electromagnetic wave which is given out. And this man, Rutherford, performed an experiment which shows that they are different and they act differently. When you take this, let's say, electrical charge and place on the part of these particular radioactive substances, I mean the emission of this radioactivity, when you have them, you realize that the beta particle is always attracted to the positive charge, and the alpha particle is always attracted to the positive, and then the gamma ray is not attracted to any of these charges, so it does not have charge. In that case, that is why it was concluded that beta is a negative charge, and then alpha is a positive charge. We are going to look at their properties. as we go on. Now, we said all particles are emitted during radioactivity. We go straight to, now this is alpha particle, and this is how it is emitted from any radioactive substance like uranium. Okay, this one is thorium. You know, when it is given out from that of uranium, you now have this thorium formed. Then this is also beta particle and all stuff. I'm going to use a table to explain these properties for us. Then on the other hand, this one is beta emission when it is given off from a nucleus of an atom. From thorium, we now have a new element formed. And this is a gamma ray. Look at the way gamma ray works. It does not have any charge, so it's just a package of wave. Like sometimes I would like to call it photon, because if you have gone through our lesson on quantization, energy quantization, you now realize that when electrons are excited, they give off a kind of radiation, which is a photon energy. Now, in this table, we are going to talk about the properties of all these emissions. Remember, we have different kinds of emission. We have alpha, we have beta, and we have gamma. Now, this table is trying to tell us the nature of alpha is helium atom. It is here already. The nature of beta particle is electron with this symbol, and this gamma ray does not have any charge, and therefore it is electromagnetic wave, just like we have shown you. The mass, what do I mean by mass? AMU is atomic mass unit. So you now realize that alpha is very heavy compared to beta. Look at beta. 1 all over 1,836 atomic mass units. That means alpha particle is heavier than beta. And then gamma does not have mass. So gamma ray does not have mass at all. In terms of effect of magnetic and electric field, that means alpha particle has a positive charge of 2 of whatever it is, the charge of the unit charge. And it also deflects when you put it in a magnetic field. It deflects to show that it has a charge of polarity. Then for beta particle has a charge of 1 unit of the charge and a very strong deflection. It deflects more with a very high angle of deflection compared to that of the alpha. Of course, you know why? Because it has a very small mass. The mass is too small, so the deflection will also be very high. And then the gamma ray does not have any charge, and therefore it does not deflect on any part. Then looking at ionization power, large, alpha is very large, has a high ionization power, and beta has medium, and this is very small. Penetrating power, I have shown you this. Penetrating power, I told you that I showed you a video for you to know what penetrating power is all about. And this is what I mean. The penetrating power, in the sense that gamma ray can penetrate, only lead can stop it. Alpha can only be stopped because only stopped by, you know, it simply means that the more massive a particle is, the less penetrating of its power. So that is for the penetrating power. Then speed, 10% of the speed of light for the alpha. Then beta is very high. The speed is high because the mass is less, so it's easily, the speed is also high. And gamma, the speed of light, which is 3 times 10 raised to the power 8 meters per second. Now, uses of radioisotope, what are their uses? It can be used in medical field, it can be used in industry, it can be used in agriculture. Then what is the use of this radioisotope in medical field? That is why there are a branch of physics these days we call medical physics, whereby people study the behavior or what happened, biological aspect of human being using physics principles. As a result of that, it has given birth to what you have, radiotherapy, and then treatment of tumor and cancer, and then checking of blood circulation and blood volume. in the body. In industry, it is used in dating geological specimens using uranium, in dating archaeological specimens using carbon-14, in liquid flow measurement, and in testing leakages, cracks, and defects in pipes. So these are in industry what you can use this radioisotope for doing. In agriculture, for sterilization of foodstuff, you preserve your foodstuff and sterilize it. Then the last one is which is radioisotope tracers and preservatives. So these are what radioactivity is in terms of its theoretical aspect. Remember, before we go, we have to look at some of the questions which have been asked by WAEC and some other exam bodies while we go to Examguide app. We are going to choose a few questions. It said, when a radioactive substance undergoes a beta decay, it's why? All right. Even though we are going to have part 2, but let's look at this. Atomic number increases by 1. Mass number increases by 1. Atomic number decreases by 1. Mass number decreases by 1. So let me give you what that is. Let's use nitrogen 14 and 7. So if it gives off, or you use beta particle to heat it, for example, even though what should go there is uranium, but let's use beta particle for that explanation. For example, you have 0 and -1 plus, -1 of this. Then plus what? Remember that in nuclear equation, there must be balance. Whatever is on this one is like the boundary separating the right-hand side from the left-hand side. So this is the boundary. So what are we going to have here? Now, I am going to look at it this way because it will help us in answering this question. On the left-hand side, we have 7 must be equal to -1 plus what? I don't know what it should be. So I'm going to be putting a new element that will be formed because of this nuclear reaction. So let me have here to say this is going to be A, Z, and X. All right, so I'm calling this one Z. So this is going to be what? You are taking 1 to the other side of the equation, so it becomes 7 plus 1 equal to Z. So this is going to be 8. 8 is coming in here. So remember, it's going to be a new isotope because this is a process of forming isotopes. So I'm still going to call this, a new element must be formed. So a new element must be formed. Remember, we want to answer this question. So the next one we are going to remember in terms of the atomic mass. So we have 14, which is equal to A. I don't know what A is. This is 0 plus A. Therefore, A must be 14. So I'm going to have 14 and 8. So let's call it a nuclide. Even though we have atomic number of 8 for an element, let's just call it a nuclide for the sake of answering this question. Now, when a radioactive substance undergoes a beta decay, its atomic number increases by 1. Of course, atomic number has increased by 1. Mass number increases by 1. No, it's still the same thing. Mass number is still the same thing. Then atomic number decreased by 1. No. And therefore the answer is A. Let's choose one more question from this. All right, let's go to this number 2 question. Okay, now let's look at it first. I'm not choosing any one. It said an element of nucleon number P. All right, remember if I have this nucleon, if this is P, remember what should be there? And this one is called atomic mass or nucleon, of course. And atomic number, all right, atomic number is here, Q. It says what? Emits an alpha particle from its nucleus. Okay, it gives us an alpha particle. This is 4, 2, helium, then plus. From its nucleus, the resultant number of the new element formed are respectively. All right. When alpha is emitting, if this emits alpha particle, the new element is definitely going to, what we are going to do first is to ensure that this and whatever element is going to be must be the same thing, because in terms of this kind of equation, which is nuclear equation, the number of atomic mass on the both sides must be the same thing. Remember that this place is boundary. So this is the boundary. Therefore, I'm going to say P must be equal to 4 plus. The new one is going to be P minus 4. So I'm using Y. So this is going to be P minus 4. Of course, this minus this is 0. Therefore, P is the same thing on the left-hand side and the right-hand side. So the new element is going to be Q minus 2. So Q minus 2 is going to be this one. Therefore, the new element formed will have its atomic number to be P minus 4. P minus 4 is here, and Q minus 2, and Q minus 2 is here. So the answer is option 2. Let's stop here for now. Thank you for being part of the class. Remember to subscribe and share the like button. Thank you.